I welcome everyone for this lecture series on electromagnetic fields. Today's lecture is about applications of Biot-Savart Law. So before moving on to the applications, we'll discuss about Biot-Savart Law. Biot-Savart Law discusses about the study of steady magnetic field. That is, consider a conductor carrying a steady current I. Now, there exists a magnetic field around this conductor. Now, Biot-Savart Law defines the effect of this magnetic field at a distant point P. It defines that the differential magnetic field intensity dH is directly proportional to the current I, the differential length dl, and the sine of the angle between the differential current element and the distance vector r, and inversely proportional to the square of the distance vector r. So in vector form, Biot-Savart law expresses the differential magnetic field intensity as dH vector is equal to I dl vector cross product into the unit vector AR divided by 4 pi into r square. So the unit vector AR can be defined using vector algebra as AR unit vector is equal to the distance vector r divided by the magnitude of the distance vector. Hence, substituting the value of AR, dH is given by dH is equal to IDL cross R divided by 4 pi R cube. Now, with this introduction, we will move on to the applications of Biot-Savart law. Today, we will discuss about the magnetic field intensity due to an infinitely long straight filament, and we will derive the expression for H using Biot-Savart law. Consider a straight conductor of length minus infinity to plus infinity, which is placed along z axis. Now, it is placed in a cylindrical coordinate system. Hence, the magnetic field intensity H can be represented as H equal to H rho A rho plus H phi A phi plus Hz Az. Now, the magnetic field intensity consists of three components. As far as our present case is considered, there are no field variations in z directions as well as in the phi direction, because in the z direction the fields get cancelled due to axial symmetry, because the z extends from minus infinity to plus infinity, and because of the symmetrical value of unit vectors in positive as well as in the negative directions, the field along z dimension gets cancelled, and the field along phi also gets cancelled because of azimuthal symmetry, as phi varies from 0 to 360 degrees. Hence, the field exists only with the variation of rho component. And now we are going to measure, consider a uniform current I that is flowing through the conductor, which is extending from minus infinity to plus infinity. Now we are going to measure the magnetic field at this point P2, which is away from the magnetic current carrying conductor I. Now, the point P is chosen in the Z is equal to 0 plane. Now, we will express the differential length dl to be equal to dz because the conductor is placed along the z axis. Hence, the current element can be written as I dl equal to I into dz, and it takes up the unit vector az because it is along z axis. And the R component is given as rho into A rho. Now we will derive the magnetic field intensity at this point P. Now consider this point to be P. The magnetic field at this point P due to the infinite current element. So with the definition of Biot-Savart law, dH is given by IDL cross product A R dlp unit vector divided by 4 pi R dlp square, where A R dlp is the unit vector of the distance vector r dlp. So it is AR dlp is equal to r dlp vector divided by the magnitude of r dlp vector. What is r dlp vector? R dlp vector is the distance vector, which is defined by the subtraction of the position vectors rp vector and the dl vector. And what is the position vector rp? Now rp, we know that P is the distant point which is away from rho distance in the A rho direction. Hence, the position vector Rp is defined as rho into A rho. and the position vector of the differential current element. So we know that our differential current element is placed along the z-axis, right? Hence the differential current element takes up the AZ direction, and differential current element is of the length in the z direction, in the direction z into AZ. Hence the distance vector RDLP is defined as RP is rho into A rho minus DL is Z into AZ. Now substituting these values and finding the unit vector, ARDLP unit vector is equal to rho A rho minus Z AZ divided by the magnitude of RDLP, where the magnitude of RDLP is the square root of rho square plus Z square. Now substituting these values in the DH component, we can write DHZ is equal to I into DL. So DL we have written as DL is equal to DZ. Hence DL can be written as DZ AZ cross product ARDLP, that is rho A rho minus Z AZ divided by 4 pi R square into DLP. So that R square is, R we know R is equal to root of rho square plus Z square. So the square root will go away. So this becomes rho square plus Z square, and the denominator of the unit vector component is R square plus Z square square root. So which is equal to, we need the magnetic intensity Hz. The magnetic intensity Hz is the integration of the differential magnetic field intensity along the entire length of the current element. Hence Hz is equal to integral minus infinity to plus infinity d into Hz. So substituting the value of dHz, we can write this as integral minus infinity to plus infinity. Substitute for dHz, so it is I dz Az cross rho A rho minus Z AZ divided by 4 pi into, this is rho square plus Z square. Here we have square root of rho square plus Z square. So combining these two, we can write this as rho square plus Z square the whole power 3 by 2. Now we can simplify this by taking the cross product of these two. And we know we are using cylindrical coordinate system where the three components as rho, phi, Z present. So the cross product of this can be written as A rho into A phi is equal to AZ, and A phi into AZ is equal to A rho, and AZ cross A rho is equal to A phi. So now we are going to take cross product of AZ cross A rho. So AZ cross A rho is equal to A phi. So rewriting this, we have integral minus infinity to plus infinity I dz into A phi and the second cross product is AZ cross AZ. When you take the cross product of the same unit vector, that will be equal to 0. Hence we have in the numerator I dz into A phi, and this rho will be present, divided by 4 pi rho square plus Z square the whole power 3 by 2. Now we need to integrate the above integral to get the value of Hz. So for doing this integration, we need to change the limits of integration. So for changing the limits of integration, from the figure, consider this. This is our Z value and this is our rho value, and here we are in the marking the angle theta. So from figure, you can write tan theta. Tan theta to be equal to, tan theta is equal to opposite side divided by adjacent side. Hence tan theta is equal to Z divided by rho. So from this we can write Z is equal to rho into tan theta. And when you differentiate this, you will get dz, where dz is equal to rho into secant square theta into d theta. And we need to change the limits of integration, where z takes up a value minus infinity and z takes up a value plus infinity. So this is to be changed, right? So from this we can rewrite theta to be equal to tan inverse of z by rho. Hence, when z is equal to minus infinity, then tan inverse of minus infinity, hence theta will be equal to minus pi by 2, And when z is equal to plus infinity, then tan inverse of plus infinity, this will give you value of theta is equal to plus pi by 2. Now we have changed the limits of integration. Substituting all this, we are going to get an equation where we can write hz is equal to integral, instead of minus infinity substitute minus pi by 2, and plus infinity substitute plus pi by 2, and we have the other components remain as it is. I, you put I, right? Instead of dz we have rho into secant square theta d theta. So we have rho into secant square theta d theta, and we have rho component here, again on rho, so it becomes rho square into a5 divided by in the denominator we have 4 pi into rho square plus, instead of z you substitute z is equal to rho tan theta, so z square becomes rho square tan square theta. So this is rho square into tan square theta whole power 3 by 2. Whole power 3 by 2 is there. Whole power 3 by 2. Now we will simplify this equation. Integral minus pi by 2 to plus pi by 2 I into rho square into secant square theta d theta into a5 divided by 4 pi into, here we have rho square as common, take it out, whole power 3 by 2 is also there. So when it comes out it becomes rho cube into 1 plus tan square theta whole power 3 by 2. So this rho cube and this rho square gets cancelled. So we have I divided by 4 pi rho, you take it out of integral, minus pi by 2 to plus pi by 2 secant square theta d theta into a5. And in the denominator we have 1 plus tan square theta. 1 plus tan square theta we know it is equal to secant square theta the whole power 3 by 2. So in the next step we'll have I divided by 4 pi rho integral minus pi by 2 to plus pi by 2, and this square and this square gets cancelled. So we have secant square theta divided by secant cube theta d theta into a5. So this and this gets cancelled. We have I divided by 4 pi rho integral minus pi by 2 to plus pi by 2 1 by secant theta d theta into a5. Then hz is equal to I divided by 4 pi rho integral minus pi by 2 to plus pi by 2 1 by secant theta is cos theta into d theta into a5. So in the next step it is I by 4 pi rho. So when you integrate cos theta that becomes sin theta integral minus pi by 2 to plus pi by 2 into a5. So substituting the limits, I divided by 4 pi rho and sin 90 is 1 and this is minus of minus 1 into a5. So this is equal to I divided by 4 pi rho into 2 into a5. So 2 and 4 gets cancelled. We have I divided by 2 pi rho into a5. Hence the magnetic field intensity of an infinite conductor carrying a steady current I is given by Biot-Savart law as Hz is equal to I divided by 2 pi rho into a5. That's it. Hope you have understood. Thank you.